Okay, in this video I'm going to continue on with my tutorial series on thermodynamics and statistical mechanics. This is video number 42. I'm going to discuss the Gibbs free energy and chemical potential. So I'd like to draw your attention to my website universityphysicstutorials.com. So to do a small bit of revision, we saw in a previous video that the Gibbs free energy, capital G, is given by U plus PV minus TS. Okay? So basically what this was we had mechanical work being done against the surroundings, and because our surroundings or our environment was at constant temperature, we could also avail of free heat, we'll say, to the value or quantity of Ts. And we found that this is at constant pressure and constant temperature. Okay, constant pressure and constant temperature. So where do we go from here? Well, we also saw that the infinitesimal change in G was going to be dG is equal to du plus vdp, it's supposed to be vdp, believe it or not, vdp plus pdv minus s dt minus TDS. That's just by the product rule. So when we subbed in the first law, we got and cancelled out the remaining term and said minus S dt plus V dP plus mu dN was equal to the infinitesimal change in the Gibbs free energy. Alright? So what does that mean? Well, if we look at this, what we're trying to do is trying to relate the Gibbs free energy and the chemical potential. So we see here this term is the chemical potential. So we notice that if we take the partial derivative of G, so say we take del G del N. If we take that derivative and we hold everything else fixed, so in this case we hold the temperature and the pressure fixed, what we get is the chemical potential. So this suggests that in order to measure the chemical potential, we somehow get an experiment that measures del G del N. Now in video number 41 I discussed extensive and intensive properties. So generally an extensive property is one which we'll say doubles when you double the number of particles, so when N doubles. Okay, and we've found that an intensive property is one which does not double when you double the number of particles. So typical extensive properties we had were pressure. Pressure usually, for example, is one which is an extensive property. But intensive properties we had things like the chemical potential, we had the temperature, and so on, right? So you just look at my previous video if you want to look at this. But if we look here, if we look here, we find that both the variables which we're holding fixed in this particular partial derivative are intensive. So both of these do not double, we'll say, when you double the number of particles. They're both intensive, E-I-N-T-E-N-S-I-V-E. Okay, they're both intensive particles. So at the moment, what this partial derivative is implying as follows. If we integrate, of course, what that means that it's implying that dG is equal to mu dN, or if we integrate both, capital G, the Gibbs free energy, is equal to mu times N. So it implies that the chemical potential is the Gibbs free energy per particle of something. So does that make sense? Well, it should make sense because we're having two intensive variables. Now what that means is, because both of them are intensive, this leaves the extensive quantities to grow with N, or grow proportionally with N, which is exactly what extensive properties do. So what we're saying here is that where you add a single particle, del G del N is the added chemical potential to the system. Okay, so that's why we say the chemical potential is the energy added to the system when you add a single particle. That's what I've been saying all along. So the point here is because these fixed variables are both intensive, as you increase the number of particles, the chemical potential remains unchanged, and that's very important. Okay, so just one last thing on this, and it's to show a contrast. If we take a similar partial derivative, if we take del f del n, so this one is the Helmholtz free energy. We take the partial derivative with respect to the number of particles. We take it holding temperature and volume fixed. Alright, now by the partial derivative, this also should give us the chemical potential. Now the next thing we need to do is evaluate, or we'll say analyze, what is happening here. So we note that both of these are neither intensive or extensive, because in actual fact one is extensive and one is intensive. So the volume is an extensive. The volume is an extensive quantity, and the temperature is an intensive quantity. Now, why is this important? It's important because as we add particles to the system, we are automatically going to be changing the volume, because the volume, if you double the number of particles, well, the volume is going to double. So this is going to change, which means the chemical potential is going to change. Okay? So the point here is that we can't actually take del f del n and use mu and get mu if, because the variables which are holding fixed, one is intensive and one is extensive. So when n increases, so too does the density holding the volume fixed, thus mu actually changes as n increases. And this is because the fixed quantities are both intensive and extensive. So to summarize then, what we say is that mu is the Gibbs free energy per particle. Okay, where we have T and P fixed. Great stuff. Okay, thanks for watching. Please pass it on to your friends, subscribe to my channel, and you might also visit universityphysicstutorials.com.